All right, I'm recording now. Hey everyone, today we're going to be talking about direct preference optimization. It's a very interesting concept. It's effectively RLHF, but better. We're going to talk about how RLHF works. So we'll understand how language models train for preference optimization from the ground up, or preference modeling from the ground up. Then we will understand the limitations with RLHF, why it doesn't work the way it should, and then figure out what are the improvements that DPO introduces in order to effectively fix that. No. Okay. So we have this background. We'll talk about intuition, motivations, deriving and understanding DPO, and then the final results from DPO. So task formulation, consider this simple conversation, right? You have a human asking you in part, what is your favorite pet? The LLM has to fill in the blanks. It says, I like dash, right? And now the question to you is, what is the correct answer? Is there a correct answer? If we look at it, contextually, right? The LLM may like anything. Anything it likes or any pet it likes is technically correct in some sense. However, this correctness may not necessarily be desirable as a property. And the consequence of that is the task of preference modeling, right? So is it dog, is it cat, is it human, or something else? It depends on our preferences. It depends on the type of the LLM that we want to create. At the same time, we still do not want it to be human. Anyways, preference modeling involves embedding these subjective biases within LLMs. And the two popular objective methods that DPO solves for is Bradley-Terry and Plackett-Luce. We will focus on Bradley-Terry today, but the general idea or the high-level idea behind these is just that you rank one preference above the other versus Plackett-Luce, which is multi-result ranking, so it ranks say 10 different preferences or 10 different options and says which one is worst and which one is best. Question.
Where did those names came from? Bradley Terry.
Oh, they're the people that developed it. It's like Brad.
Long time ago.
Huh?
Long time ago.
I don't know. I take it for granted. But I mean, if I had to look it up, maybe I can find something. Bradley Terry. I don't know. Probability model. Give me citations. 2004. No, generalized Bradley Terry model. Which one? Oh yeah, there we go. Yeah, 1950. So yeah, it's fairly recent. But yeah, there's Plackett-Luce, which is multi-result ranking, and that's from 1 through n, where n is the total number of options that you have. We'll talk about Bradley-Terry, as I mentioned earlier, just because it makes the solution a bit more straightforward to work through. However, it exists technically for Plackett-Luce as well, and the paper actually derives it. So the synopsis of RLHF. So we'll review this pipeline per Ziegler et al. It has 3 primary phases. The first one is supervised fine-tuning, where you have a pre-trained language model that is trained on high-quality, domain-specific datasets in order to obtain pi SFT. Pi is usually used in reinforcement learning literature to demonstrate a policy. In this case, our policy is a large language model. The domain-specific dataset is important because if you are trying to create an LLM that is able to, say, give you legal advice, you definitely don't want to do that. But if you do, you at least want it to perform to the best possible capacity. So having a supervised fine-tuned model is very important to improving on a pre-trained model that is trained on a massive corpus. However, you can technically skip this step, although your results may vary. Next is the reward modeling phase, where we create a reward that is parameterized by phi, x comma y, that models user preferences. X is the input, y is the output, or y is a potential score. Sorry. So we set up a data set where we have x sub j, y1 and y2 for n samples, and we create a this data set is basically just prompt and option 1 versus option 2, and this is sampled from the supervised fine-tuned model where we basically request two outputs and then a ranking for which one is preferred. And then we have an unsupervised data set, which is, or not unsupervised data set, but an unsupervised set of inputs, which is x sub, denoted by x sub I. And the preference modeling is basically y sub w for winner, better than loser, given input x. For r star x comma y, this is our optimal policy. This policy is unknown to us, right? This is the true answer, and exists for every single type of input. This is not known to us because it's ground truth basically, and this is what we want to ideally obtain. But we approximate this using the R sub phi. Per Bradley Terry, the probability of y1 being greater than y2 given x is, or greater than here is for preferred to y2 given x, is basically the softmax for y sub 1, and then this over the r star, which is our optimal policy. Yes.
To make sure, supervised fine-tuning is a self-supervised masking training process.
So you can use masked language modeling as well, but the typical approach used today is causal modeling. So that's what is usually used. But yeah, that's both are options. I think MLM though is for encoder only, or like encoder decoder models. For decoder only models, I am very confident that the causal approach is what is usually used.
So it will be last token, right?
NSP, next sentence prediction, yeah.
Okay, so it will be the next sentence or next token?
I think it's NSP. I think it is next sentence prediction. It basically till the end, right? Till the end token. So until once the auto-generated process is completed, when it returns the end token as a output, correct? So basically, I presumably it goes to the end token with a ceiling for max number of tokens to generate. So if it doesn't generate the end token after some point, it clears or it ends the sentence, and if not, it just returns whatever the subset you output.
Sure. So it will be this supervised learning. So there is a ground truth text, and then it's going to do the SFT supervised.
Yes.
And then so the reward modeling, the R is the output of R is a scalar.
The output of R is a scalar.
It's a scalar, and then we also call it a policy. But just in the context, the paper also talks the policy of that we're trying to optimize is actually the language model. It's not really the R, right? The R is one scalar, but the R
is fundamentally the language model. Yeah, that's the exact next thing. So over here, this point B is basically what you're saying, right? Yeah. Right.
Yeah, and then the R is also coming. The model part, the model of the R is also coming from the language model, except for the last layer. We just cut the last layer and then connect to a scalar. That will become our R in the original RLHF.
Yes, that's exactly what that is.
Okay.
So yeah, perfect. Going back just a little bit, we have the R star x comma y is our unknown optimal policy, and this is the kind of equation 2 is basically our test setup for the actual data set itself. Now this I spoke about. This is the preference distribution, and we optimize this over a negative log likelihood, and we maximize negative log likelihood to get a best performing model. This best performing model is parameterized with R sub 5 x comma y, and some notes about this. The rewards are normalized over x in order to motivate lower variance. So the expectation of the reward over all of x is 0. And the second thing is that R sub phi is the supervised fine-tuned model with an additional linear layer that just returns a scalar reward rather than another token. So you just swap the final layer with the single scalar value instead of the softmax over the entire vocabulary. Yes.
The rewards is normalized, so it means that the mean is 0.
Yeah.
It's a little bit confusing. Why the mean of the reward? The
So there are a couple of reasons for that, but one really cool thing that I have been reading recently. So I was supposed to present omni predictors today, right? Which is a paper that talks about robustness in order to get that sets up the notion of an omni predictor, where instead of minimizing to a single loss function, so for instance we have negative log likelihood over here for our reward, instead of just maximizing that loss, what we do is we maximize over a set of convex loss functions, and what that allows us to do is generate a universal predictor, and this predictor is and this predictor is optimal, or not optimal, but at least performs better than the expected loss over the model trained on a single loss function. Okay, and I read deeper into the entire thing and realized that I do not know it well enough to present it. So instead we're talking about DPO. But what I do understand is the notion of multi-calibration that it also talks about, and this, in my opinion, is an effort towards getting that multi-calibration. So what multi-calibration is this sort of example where we have this set of outputs, and we model this with these certain subgroups. So we have this subgroup 1, 2, 3, and then 4, and also 5. This creates or constitutes our entire data set, right? Now the likelihood for, say, a binary task, right? Let's say we have classifying cats versus dog, right? We try to classify the probability of the image being a cat and an image being a dog. Let's say our data set entirely has 50% cat, 50% dog, right? Then over here you can see the average prediction is 0.5, correct? Now the idea is that this is a multi-calibrated model, wherein if I give any input and just ask it to give an output, it gives 0.5. This is technically a multi-calibrated model in the sense that it is correct, because for the entire distribution, 50% of the image is cat and 50% is dog. So that is correct, but it is not helpful at all because we don't learn anything from this, correct? And the idea behind multi-calibration is you have these subsets of groups, wherein under this group, right, you have the likelihood of the image being a dog. So let's say over here the probability of the dog is really high because this group contains the image of the dog. So there are a couple of cats that look similar to dogs, but most of them are dogs. So there is a 90% chance that if we classify under this subgroup, the output is a dog, and the rest of it is the 0.05 and 0.25, 0.125 and 0.125. Hopefully this adds to 1. If it doesn't, I'm bad at math, so consider that. In any case, we have these subsets, and this entire thing constitutes our entire universe, right? So now over here, if I give some point over here, the idea is that this point, the probability that you should get of y for this point within where x is within subgroup 1 should be 0.9, right? This is the notion of a multi-calibrated model. Now, if we do not explicitly try to embed this notion of multi-calibration, the idea is that you have to explicitly state why you think that the probability is greater than 0.5. 0.5 needs to be your baseline, and if you are saying that the probability is more than 0.5, you have to justify that, and that's the basic idea behind multi-calibration. So what I think that this is doing via normalization, in addition to just minimizing variance, it also ensures that the system is calibrated to a certain extent. Although that makes it weaker overall, it makes sure that it is consistent, which is important. Question, you raise your hand first.
What's the difference between this and, like, let's say any sort of binary classification model that just weighted the cross-entropy loss? Like, let's say, like, whatever if it's like the distribution skewed towards 0.9 for dog versus 0.1 cat.
For your entire data set?
Yeah, but like to me, like this just sounds like I partition it 5 ways, and then for each of these partitions they have a different weightage.
So the key difference over here is we are not specifically just saying 90% of dogs you go in this image. There is some underlying similarity within the data that it causes certain images to go within subgroup 1, some images to be within subgroup 2, subgroup 3, so on and so forth. So for instance, this is very much more relevant example would be for the medical field, because there are a lot of patient subgroups, right, that you can split based on age, race, gender, etc. And in this case, or in that specific space, it is very easy for us to create these subgroups, and the likelihood of a certain prediction within a specific subgroup might be very different for different groups. These groups exist within image data very significantly, but it's just not something that we explicitly know ahead of time, which is why they tend to get grouped up into this like mega group or this universe, and we don't consider the fact that there is this subset within this that causes it to change drastically, and that creates a problem further down the line.
Okay, that's cool. Thank you.
Mm-hmm.
Okay, so I originally had a question like that, but another question I have is how do you make those groups if you don't know exactly what your data is? Like, for example, if you're an LLM, you can enter anything into that, right?
Right.
So you can't really classify that as let's say by gender or race or.
Yeah, exactly. That's the entire thing. So it is a very awesome question that you have asked, and it's something that I am trying to figure out with image data, because I mean, this is a tangent, but images have a lot of data by default, right? So if I give you say 3 images of a fox, you will be able to identify a fox in the real world without any issue. But CNNs or any vision model really requires at least thousands of images in order to do so reliably, even if it is already been pre-trained on and has like a world model internally. And that is partially, in my opinion, because these subgroups exist but are not identified at all by the model, which causes it to perform very drastic, like poorly in situations where the training data is not substantial enough for the subgroup to play a precedence. Right? So over here, if we were to use something like a regularizer, a very strong regularizer where you want to minimize the number of parameters used in the model to motivate generalization, what usually happens is this 0.9 gets very highly prioritized, because knowing the fact that this subgroup is 90% of dogs is already more than enough for any model to perform with a very high amount of accuracy, at the cost of subgroups 2 through 5 being very low accuracy, right? So for instance, if our universe model of cats and dogs in the dataset was 90% cats and then 10% dogs, if the model just predicts cat every single time it was asked a prediction regardless of the image, it's going to be correct 90% of the time, right? But it's effectively useless, and that's kind of the notion within or like that multi-calibration attempts to fix, where you need to have something meaningful in addition to the base probabilities in order to get a meaningful improvement. And for language models in this case, right, since we don't know what the subgroups are, if we just calculate expectation and make sure that is normalized, we are effectively doing the weakest form of multi-calibration, where technically this is multi-calibrated but not very informative. And that's kind of the idea behind having this parameterized reward function. And in addition to that, more realistically also, or like the more, I guess, practical application of the of minimizing variance is also so that certain rewards don't utterly dominate, right? You have it between a bound so that you don't have gradients that either explode or implode. Yeah. So that helps as well. Okay, awesome. One more question.
Yeah, very quick.
No problem.
So a paper said expectation of the reward equals 0.
Yeah.
It means that some rewards are less than 0.
Yeah, because it is normalized. So it's between like 0, 1 normalization, right? If I have over here, we have some rewards like this. This is a bell curve. Obviously, I don't expect the reward function to be a bell curve, but just as an example, most of the rewards are centered around 0, and the mean reward over here is going to be 0 because there are some positive, some negative.
And this is a supervised learning to train the reward model. And
yeah. the human does not give the score. The human only gives a preference. So it is presented y sub 1 and y sub 2, which are two responses for a prompt input x, and it has to just pick one that makes the most sense.
But how do you train it though? The output is a scalar between
yeah,
zero.
You prefer one and you prefer one over the other,
Yeah.
and then you have the I think the reward training procedure is over here. So nope, one second, let me read. R sub star is the unknown policy. We have the Bradley model. Oh yeah, here. So we have the softmax of this, right? This is the probability conversion of the preference to the probability.
Conversions of the
Preference to the probability. So if I go to the paper, they explicitly talk about, like they make the softmax thing more explicit. So over here we have this, right? The preference distribution per Bradley Teddy. This is the equation that it uses. It's basically just you run softmax over it and pick the preferred model.
Sure. So the P is going to be a point something. It's a less than 1, right? And then there's going to be a label to train on, right? Calculate the loss.
Right.
And then that
The label is the reward.
the reward has to come from the human, right?
No, the reward does not come from the human. The preference comes from the human.
0 and 1, right? 0 and 1.
Yeah, fair,
And then,
yes.
And then the model output is a scalar with a mean of 0. It can be minus 0.1. It can be
Positive, yeah.
positive 0.1.
Yep.
And then what is your label to train it? It has to be a supervised learning, right?
Yeah, the label is in equation 1 over here. We have the you run softmax over the 1, 0 vector,
Sure.
right? Get the
But R star is the
optimal. Yeah,
It's the optimal. We don't have that.
we do have that. It's supervised, right? So we have the output of R star x comma y1.
We don't.
We do.
We train it.
We have the subset over R star. We don't have R star. So the R star is basically our human labeler. We assume that our optimal is whatever the human has labeled, right? That's our ground truth. Does that part make sense? I'll explain further, but
Okay.
are we in agreement on the fact that R star is sampled? In order to sample from R star, we basically ask a human to label it.
We have the Y win and Y lose from human.
Y win and Y lose from human. Correct, right?
So 0 and 1, right? Win and lose. But R star X Y L. We
Yeah.
don't have that.
We do have that because we give we have got, okay, we have X is your favorite pet, right?
Yeah.
And then we get Y sub 1, which is cat, and Y sub 2, which is dog, okay? So we as a human labeler have to say, is Y sub 1 better than Y sub 2?
Perfect.
Or is Y sub 2 better than Y sub 1?
Yeah.
Let's run a quick poll. How many people like cats here more than dogs? How many? We have just 1, 2, okay, versus 1, 2, 3, 4. So, okay, dog wins. So, we will say that dog is improved or better than cat, right? And we assign 1, 0 like that, right? And now we want to get the softmax over this. So we compute softmax of this, right?
R star.
R star is the reward policy. That's the human. We are not computing softmax over the human.
So
We are computing
what is the
softmax over
of
the
this? What's the softmax of this?
softmax of this. It's okay. Wait, I think I can figure this out. E sub 1 over E sub 1 plus E sub 0, right? That's our preference distribution. So
So that's the label.
2.71 divided by 3.71. This is 71. This is numerically what it would become.
So this is the label.
This is the label, correct? Yeah, that's our label, right? This is our reward. Now we want to, on the basis of this, generate a function that will give me a reward for 2 options, but I don't have the answer. or not two options, but I don't have the answer, one option and I don't have the answer, right? Just score this response. Is it a good response or a bad response? You have to figure that out. It is centered at 0. So if you think it is a good response, it will be over 0. If you think it's a bad response, it will be less than 0, right? That's the general idea.
Okay.
All right. Do we have any more questions? Everything makes sense so far. Okay.
Policy regarding, are we at the policy part yet?
Yes. So policy for in RI literature means just a specific action taken given input.
Yeah.
For our case, it's an LLM. So the action is the response or what the LLM outputs. So whenever you see pi, you can assume this is language model. That's pretty much the same thing. For our purposes, at least for this case, it's the same.
Okay, so I have a very elementary understanding of like anything R related. I think about state space, right?
Uh-huh.
How does that space mapping kind of work in a like language response? Because I would think like, okay, if I, let's say in a game environment, I move up, right, left, up, right, or down, right? And then I get the reward based on the policy, like moving on each
Right.
side.
Right.
How does that work for language though? Or how can I think about it?
So we have the X over here, and it has to give an output. So the state space is the entire vocabulary of the language model. No, the state space is the input or whatever tokens are there within the context, right? And the action it takes is the response. So it has 36,000 words in the vocabulary. It can output any one of those 36,000 words, right? So over those 36,000 words, there is a reward function that says that for this response your score is 5. For this response your score is -5. I do not like that. So that's the general idea. And now we have the state space, we have the action, and we have the reward, and we optimize it, optimize the model to give the best action such that the reward is maximized.
Yeah. Okay. So the model is approximating the best policy, right?
Yes, the model is approximating the best policy. Exactly. Cool. More questions? No? All right, I'm going to move on then. Finally, we have the fine-tuning procedure, right? So we have this reward model that we have trained using supervised learning. And now we want to maximize our sub file by using the language model. Our assumption here is that this parameterized representation of reward that we have created is equivalent to our optimal reward policy, because we are going to try to run inference on samples that we have not seen before, and our assumption is that it works basically. So that, and importantly, we don't want mode collapse, which is basically random tokens that maximize reward. It's basically a form of hacking for the model, right? It would be like perturbations wherein the new policy that we obtain will maximize the reward technically, but it's going to find a loophole within our parameterized reward function to just output random tokens, and it will give it like a very good score, which is something we don't want, obviously, because we still want our models to make sense. So the solution for that is KL divergence, and this sets up this min-max problem where we want to maximize the expectation of X sample from the data set and Y sample from the parameterized model, which is pi sub theta. And this allows us to get this reward function, which we want to maximize, and we want to minimize the amount of KL divergence that we have from the supervised model pi sub theta, or like the fine-tuned model pi sub theta, which we are training for, versus pi sub SFT, which is the original supervised fine-tuned model. So the supervised fine-tuned model is going to give us an answer that we know makes sense as far as the language is concerned. We know for a fact that pi sub SFT is going to give us an output that syntactically is correct because it doesn't have mode collapse. And we want the answer or the response to be as similar as possible. If it is different, it should justify that with an improvement in the reward. That's the general idea behind RLHF. Question?
The R5 is the reward model, and then it outputs a scalar, right?
Yes.
And then it's fixed right now. We already did that training in the step 2.
Yep.
Right now it's fixed.
Yep.
And then here, we try to maximize the expectation by having a scalar minus a KL divergence of given X, Y. So pi language model.
Pi theta is a language model. Yep.
And then pi SFT is
yeah.
the base language model.
Supervised fine-tuned language model.
The original one.
In step 1, the one that we got in step 1. We have a pre-trained model, that's our original one, and then the supervised fine-tune is step 1. This is from step 1.
Diverge from, so if pi theta starts with the SFT.
Pi theta starts with SFT, correct.
And then it starts to diverge.
Yes.
But it cannot diverge too far so that it still makes sense syntactically.
Exactly.
And the question is, if the y, is it a y win or is it a y lose? Because my goal is to maximize the expectation. If y is the losing, not the preferred answer.
We don't have the options anymore. In this case, we don't have an option or we don't have like a preference anymore. We just have the huge set of unsupervised data k over here. So in equation 1, there is x sub I k, right, in the set of size k. That's our data that we are going to use for the fine-tuning procedure, right? But or the reinforcement learning procedure, right? The original data with the preference that is used in the reward modeling procedure.
So this is not using the reinforcement learning, right? This is the reward model.
Yes, exactly. So this reward model, the data set is there for that, and then the x sub I data set is for the fine-tuning procedure.
So in the final step, the reinforcement learning part.
Yeah.
There's no differentiation between the losing and winning y anymore.
There isn't, no.
But what if I input a very bad losing y?
Yeah.
It's still trying to maximize the.
It is not. That's the part. So that's the idea where R sub phi comes in, right? Because we have, if we go back to the equation, we see the y output that is output that we get once we sample from pi sub theta, correct? And then we run it through the reward model, right? So we have R sub phi x comma y. Now this R sub phi x comma y is parameterized, and the idea here is that since we assume that it is the optimal reward, it should give a very bad score to it.
Do the R5 and pi theta, do they share the same parameter at the beginning of this step 3 fine tuning, or they're already different?
R sub phi and
R theta, because R theta also use the exact same weights in the very beginning, right?
R theta we don't have R theta.
Oh, so sorry, R5
and
R5 is also.
So R5 is our supervised. So let's say we have the LLM over here. I'm just going to treat it like a huge brick, right? And then after that, at the final layer of the LLM, we have the final softmax layer, right? So this is over the entire vocabulary of 36,000 tokens, and then we run softmax over this to get the predicted output. This is our the pre-trained model. In order to, not pre-trained, this is our supervised fine-tuned model. In order to generate our reward model, we use R sub or like pi sub SFT, and then over here the final output is just a scalar.
Yep.
So all of this just converges to one single point, right? And then over here, this output from this whole thing, this is what do you say? This is R sub phi.
So this is no longer SFT because the weight has been changed.
Yes.
Yes. So the weight has been changed, and then the pi theta it starts with the pi SFT, right?
Pi theta starts with pi SFT, correct? It
So
does not start with R sub phi. So the weights are generally completely or like significantly different. I think it is in certain cases the pi entire language model itself is frozen, and then only the last layer is trained. Right, for like as transfer learning purposes in certain cases, and I know in certain cases that it's also you just train the entire language model as well.
Is it frozen or is it trained?
It depends. Like there is no one size fits all solution. I think you can consider it either way. It should not change the understanding too much.
And so y, if I look at the equation, y is sampled from pi theta, right?
Y is sampled
from pi theta.
Pi theta. Correct.
And then, because pi theta starts with the SFT, so it can generate a very bad answer.
Yes, it can generate a very bad answer.
And then I'm trying to maximize the reward of that very bad answer.
Yes. You want to maximize. You don't want to maximize the reward of the very bad answer. You want to just you want to maximize the policy to give a very good answer. So we're not changing the reward anymore. We're changing the language model.
But if I look at the equation, y is a bad answer, and then
Okay. Yeah. Y is a bad answer.
y is a bad answer, and then I'm trying to maximize r5.
Okay. Let's go through this. We have the equation. I'm going to not walk through so much again. Let's just say we have expectation of r sub phi x comma y, and then this is subtracted by kl of the distance of pi theta, and then, or like, no, not pi theta, the response from that, and then the distance between pi sft, again y x, right? So this is our divergence term. We want to minimize this, right? And then this is our reward, our expected reward.
It's already fixed.
This is not reward. This is not fixed.
This is because r5 is already trained.
R phi is fixed.
Yes.
R phi is fixed, but it's a model. You are running inference on this model.
Sure. So everything with different x and y.
Yes.
You can only get one reward, one scalar.
Perfect. Yeah, absolutely.
Sure, but I get a very bad losing y.
Right.
I'm
So
still trying to maximize it.
we are not trying to maximize it. We want to maximize the expectation of the reward, right? By maximizing expectation, what we are saying is we want to make sure that R is as high as possible, so that our expectation is as high as possible, right? So if we have x comma y, and this is very very bad, so this is -4, right? This is minus reward. Our final equation is going to be, there is going to be some amount of divergence. So let's say we have a 0.4 divergence and we have -4 over here. So the final reward that we get for this single sample is -4.4, right? Now this is bad. We want to make this reward higher. So this is the negative feedback that we are giving to the model, and it tries to correct this over the entire data set. Oh shit.
So it will be, wants to make it higher, maybe make it like a -3.
Away from my laptop, yeah. -3, yes, we want to maximize it. But the thing is over here, in this scenario, if you end up with a negative reward at the end of it, that's bad, because that means that your supervised fine-tuned model is better than the model that you are running right now. Well, actually, no, that's absolutely wrong. Nope, even a negative reward is better if it is an improvement. But since we know that the reward is normalized, we definitely expect the reward to be a positive value and not a negative value. Probably something is wrong if you are getting a negative reward, but technically if there is an improvement, I think that is still should be better. Right, okay. So far so good? Makes sense?
I'll ping you afterwards.
Okay.
Yeah, because it's the expectation part, mathematically I'm still not very convinced, because you're still trying to win or lose, you're trying to maximize the whole thing. Expectation of it, right?
Right.
It can be a good output, it can be a bad output, but expectation of it.
So if the reward is, if the output is good by the model, we will maximize the reward will be positive. So the model will get an intuition to say responses that are like that. So in the case of our cat versus dog scenario, the idea would be to say we do when the model outputs, we can get 5 samples for the same input x as an example, right? You can have a dog, cat, parrot, sparrow, whatever, and then you will ask the reward function to rank the rewards. It will have a very high value for cat and a very low value for everything else.
Because it's negative, so because it's negative, by maximizing the overall the sum of it, it will try to make the negative more towards 0.
Yes. Yep.
I see. Good.
Okay.
Yeah.
Now makes sense?
Yeah.
I'm happy. Cool. This is equivalent to the following reward function, which we maximize using proximal policy optimization. If we just look at the reward function over here, this is the r sub phi x comma y, and then again just KL divergence in the actual equation with the actual equation for KL divergence. That's our reward function. We maximize the reward using PPO, and that's RLHF. Now let's go to DPO. So the primary.
I want to go back one second.
Okay, yeah.
So all we're saying here, just to repeat what Vishal was talking about,
Uh-huh.
the expectation of the first formula is literally just saying that whatever this reward value will estimate, whatever the policy that we generated for this x, y, assuming that that could be high or low, but we really get punished for improperly rewarding a wrong guess as high when we do the KL divergence, right? Because the two distributions would be far apart. Is that the right way to think about it?
One more time. Sorry, I didn't follow.
The first part of the reward, right? The reward R5 XY, right?
Yeah.
All we're saying here is that whatever we generate a policy and then we're just gonna rank it on whatever this like state space label is, right?
Uh-huh.
So that's some reward, whatever.
Perfect.
Okay.
Yeah.
Now, help me understand the KL divergence properly.
Yeah.
My understanding is that it shows the difference between two distributions, right?
Yeah.
And so if I'm getting a good like the main fault with like I guess rewarding the losing guess, right, or the y lose, is that the pi phi of like okay, I forgot pi theta.
Mhm.
That's the parameter list. Which one is that?
Pi sub theta is the model that we are training. That's the output model. Yeah.
So if our approximation is very different from the like the SFT, right?
Uh-huh.
That's where we get the larger margin of error. So like my point is to say that we don't actually get the big error from the reward for like giving a high value y lose, but actually the KL divergence being larger, right?
The KL divergence is not for reward. It has nothing to do with reward. The idea is to prevent mode collapse. So let's say, for instance, we have I'm just going to use the same x, right? Now let's say the y output that this model gets is like Apache helicopter, right? That's not a pet. So this is definitely wrong, right? And if I want to take this over longer sentence context, that becomes an even bigger problem where it can just spit out random words that don't make any sense, like Windows is good, and sentences that are not syntactically correct. For sake of correctness, Windows is good would be appropriate, but it shouldn't be grammatically correct, is what I'm trying to say, right? So if you get this series of outputs or this series of tokens which is grammatically incorrect, there is a chance that just by perturbation the reward model gives it a very high score, because the reward model is not considering the grammatical correctness of the model. It is only considering the reward function specifically. So it is just giving a single linear output, like single scalar output, right? So because of that, it becomes very what do we say? It becomes very I'm missing the word. It just becomes at risk of mode collapse, right? There is a better word for this. I just don't remember it. Anyways, the idea behind no, it's I'll get back later. Anyways, the idea is the same still. We are trying to prevent mode collapse, and the way that we prevent mode collapse is saying that we want to keep the reward, we want to maximize the reward while making sure that our current model is as similar grammatically. So the distribution of all of the tokens should be as similar as possible to the distribution of the regular supervised fine-tuned model, and it should still be grammatically correct, right? So the idea is that we assume SFT model is grammatically correct, and if it is deviating too much from the distribution of the supervised fine-tuned model, we are saying that, oh, there is something wrong over here, it is forgetting English, right? That's mode collapse. And the KL divergence is just trying to minimize the amount of deviation, which will help get the preference without forgetting English.
Okay, so we're saying that like as we recursively expand the language, we're making sure that distribution of like what English language sounds like doesn't go too far off.
Yes.
Okay.
Yes, exactly. Awesome. So if for a very simple example, if you were to consider cat and dog, right? the idea for the distribution of tokens would not change very much if we want to maximize a reward for someone that just really loves cats, right? The only probability that should change would be that of cat, which increases, and dog, which decreases, right? And we'll see this exact idea in DPO, just expressed in a different way, which is a part of what makes it extremely awesome. But that's RLHF. Do we have any more questions for RLHF? No? All right. Okay, let's move on then. Now let's talk about why DPO, why RLHF is bad, right? So far it seems pretty nice. The big problem is that language generation is discrete, and the consequence is that not language generation, that's incorrect. Not language generation, it's the fact that we have to sample from the reward model. And sampling from the reward model is a discrete process that makes the objective non-differentiable, and that's why we cannot just directly optimize it. We need to use reinforcement learning or PPO in order to optimize the fine-tuned language model using reinforcement learning. Yes.
What do you mean by the language generation is discrete?
Over here, no, that is incorrect. That is misinformation. Ignore that. What I mean here is that we need to sample from R sub 5, which is what makes it, for every single example we have to sample from R sub 5, which is what makes it discrete, and having pi sub theta at the bottom over there within expectation as well requires us to optimize it discretely, because the search space becomes discrete.
And the slides said it's non-differentiable.
Yes.
You mean the reward model R sub 5
Yeah.
is non-differentiable?
The generation of this entire expectation is not differentiable. We can't differentiate against this expectation because of the first term. We have R sub 5, which is a parameterized model, and the Y is sampling from pi, right? Which is the problem.
Yeah.
Pi sub theta.
This is a neural network. R sub 5 is a neural network. Why is it not differentiable?
We are freezing the parameters.
Sure. It's not trained in the fine tuning here in the RLHF.
No.
And only the R5 parameters are updated, right? And it can be treated as a constant. So
It cannot be treated as a constant.
why?
Because it changes based on the input, right? Otherwise, it would not be a loss function. We could differentiate, if we differentiate against a constant, that would be 0, and then we are only minimizing KL divergence, which is 0 for the exact same model. So that for like SFT, so there nothing would actually happen then.
And how would they do this training then? How would they do that?
Using PPO.
Yeah.
We can go into PPO. I think we are short on time, but I can. I can show you the basic equations. That's not right.
So it's able to handle the changing R sub 5.
Yes, PPO is used to optimize the reward model, right? So if you go here, TRPO, clip surrogate, yeah, here we have. This is the PPO algorithm. So we will not talk about this too much now, but if you want to look at how PPO will optimize this language model, that is how we would do it.
But the PPO is not, in that paper, the PPO is not actually optimizing the reward.
It's not optimizing reward, it's optimizing the policy, the model.
Sure.
Yeah,
The language model.
you're correct.
And because it's based on the trusted region, right? It's based on the DPO, and then it's only adding the clipping function in the PPO here, right? It's but the thing is that it doesn't actually address the problem. It's non-differentiable. R sub 5 is non-differentiable. It still doesn't address that problem.
How come? Well, the R sub 5 is non-constant, right? As we discussed, which is
And then using PPO can solve that.
Yeah, PPO will just PPO is performs optimization over discrete space, right? And this is a discrete space, which is it's not it's a non-continuous space. At least I know that for sure. Right? We don't have a guarantee over the continuity of R given X, right? So or R sub phi given X, which is why we can't just directly optimize using maximum likelihood. Right? Okay. So then we use PPO, and then we have like a good model, right? But the problem is that PPO is first off suboptimal. It also requires us to deal with the normalization term. So despite us normalizing R sub phi, we still have to deal with high variance, which in certain cases causes instability. If you read PPO, they will all the paper itself will also tell you that it is relatively stable, but that relation is to other algorithms like TRPO, not something like MLE. So it is like a bit of a context which that we have to sort of go through to understand that saying like a reinforcement learning technique is stable is can be very different based on the type of problem that we are looking at or the type of optimization strategy that we are looking at. So this can be learned or sampled by human completion baselines and then normalized. Again, this is not ideal though. DPO creates R sub phi that enables the optimal policy extraction in closed form, which is awesome. And the optimization policy that we get represents both the language model as well as the implicit reward, which is why we don't have the issue with the divergence and mode collapse. And that is also why they say your language model is secretly a reward model.
In this equation,
Yeah.
It says actor critic algorithms are not stable.
Yeah.
Is that expectation, that equation is the actor critic?
Yeah.
So which one is actor, which one is critic?
The critic is R sub phi and the actor is pi SFT.
Critic is what?
R sub phi.
Okay, and then the actor?
Pi SFT. Not pi SFT, pi sub theta. Sorry.
And then the actor never change.
The actor,
Well, the actor.
the critic never changes, the actor changes. The actor changes to make the critic happy.
And in here, does the actor doesn't update. It doesn't update the parameters. Only
The actor does update the parameters.
Is the critic static?
Critic is static, yes. Critic is the reward model.
So that keeps it.
okay. So the R phi R sub phi is the critic,
Yes.
and then the actor is the R sub theta, and then
The actor is not R sub theta.
pi theta.
Yeah.
Pi theta is the actor.
Yeah.
And then it's updated. And
Yeah.
then the critic doesn't update.
No. Yeah.
Shouldn't both R sub theta and pi SFT be the critic because pi SFT is also constant?
Pi SFT is not criticizing the output of
It's just like
of
what
the-
you're comparing it to.
yeah.
Oh,
So the critic is taking as input the output generated by the by pi sub theta, right? Which is our fine supervised or which is our RLHF fine tuned model. Pi SFT is only used in order to minimize deviation between the output of pi sub theta. Well, I mean, I guess in some sense you can say that it is technically critiquing pi sub theta and making sure it is similar as possible. So actually, semantically, I think that argument also does apply. Yeah. So I guess we have two critics and one actor.
How do you get from the previous equation into this? The previous one is the KL divergence one, the expectation of the reward minus the KL divergence, and then how do you go from that to the actor critic version of it?
This is just the normalization term. The actual expectation is exactly the same.
Is the same equation?
Yeah.
A reward model minus the KL divergence. And
Yeah.
then the KL divergence can be expanded into
The sum over all y and then the pi SFT raised to the exponent of R sub phi, which is the reward, over divided by beta, which is the normalization term.
it can be broken into
Yeah. All right, cool. Now let's actually get to DPO, right? One more, just a bit about the high level. So we've gone through all of RLHF, and we are using maximum likelihood to get a reward model. Then we are using that in order to train a language model to work better. But in DPO, we are just directly using preference data in order to like to fine tune the language model, and that's our final step, right? There is no intermediary. So that's our objective. We want to transform from loss over reward to loss over policy. So first, we must identify a transformation that takes pi SFT and the reward function and gives us a valid probability distribution P star, because then we can just directly get or use P star, or not P star, pi star as the target representation or the target distribution of the language. That itself gives us our final answer, and we can use MLE, like maximum likelihood, in order to get a language model that is preference tuned to our new LLM. So we use this in order to construct a loss over the DPO, which maximizes the negative log likelihood over the KL divergence of pi sub theta with pi star, which is our optimal policy. And then if pi sub SFT is not available, actually this is actually a side note, but if we don't have a supervised fine-tuned data set and just have like some preference information, we can obtain a supervised fine-tuned model by just training the pi sub by just training the pre-trained language model over the preference data to get a maximum likelihood estimator. Yes.
Right now, the goal is trying to get rid of the R5, right?
Yes.
We don't want the R5 anymore.
We don't want alpha anymore.
Because it's hard to train it's not differentiable.
Yeah.
And the actor critic is kind of complicated. And right now, after we get rid of the R5, here it says we first identify the high star. And
yeah. This is a high level, so we'll talk about how we go from pi SFT comma R to pi star. But the high level idea or our goal with this paper is to transform the current paradigm, which requires us to have a language model, a reward model, and a policy, into a new distribution that represents the reward while also remaining a valid probability distribution, because then we can use it, treat it like the output, the resultant output.
what is a probability distribution? So it will be a bunch of numbers from 0 to 1, and then sum up to 1, and then that is.
And all values are greater than equal to 0, yeah.
And then we call that the valid distribution of what? Of the token or of what?
Yeah, of the token. So we want this new updated valid distribution over the entire vocabulary. That's what we want with pi star.
So the pi star is a bunch of, is a vector. Can I say it's a vector?
Yes, it is a vector.
Of 36,000 words.
Yep.
And then sum up to 1.
Yep.
And then we get that from the pi SFT.
Yep. And R.
And R. But R, we don't want it.
We extract it, we extract it in closed form. We extract the reward model in closed form and then MLE over it. We'll see how we do that exactly. But the high level idea makes sense, because we still have to factor in the reward itself, right? If it's invariant to reward, then we are not actually doing anything with the reward. It does not have any value. But we want to represent this reward in our new probability distribution that we create.
So the final output is a vector of size 36,000.
Yes.
Sum up to 1.
Yep.
That is the probability distribution we want.
Yes. Exactly. Awesome. So we have that. When pi SFT again is not available, we can just use it. We can just create one by training the pre-trained model over our preferred data. Not ideal, but it minimizes distribution shift, which is good. So now finding that transformation, we start by restructuring the maximization objective that we saw previously with RLHF. We have the original reward, we have the KL divergence over here, and now we are minimizing the same expectation over the log of pi sub theta y given x over 1 over z of x, which is a partition function, effectively contains our normalization term that converts just a series of real values into a probability distribution. Then we multiply that by pi sub sft y given x and raised to the exponent of the reward divided by our beta, which is a hyperparameter. We subtract that with negative log c of x. From there, we go, or actually to explain it in English, that is just over the equation or beyond just the equation itself. The maximization objective is the reward minus the KL divergence, and the maximum to the minimum objective, the transformation where we went from maximizing to minimizing, is because we are just doing divergence minus reward, and we can combine reward and the SFT model by plugging in a partition function. So if we go to the appendix, they have a detailed proof of how they go to how they obtain the new reward function or the new partition, the new probability distribution from the original KL divergence. We have this same thing that we started from over here. We do reward minus the KL divergence. This is the default that we have. We make the maximum minimum, so that's just swapping the reward function with the KL divergence. And then we say the pi ref, which in this case is the supervised fine-tuned model, or pi y sub x, which is the model that we are trying to create, divided by pi ref, which is the definition of the KL divergence, can be re-represented by pi sub theta y given x divided by 1 over the partition function. And we can see that the partition function over here is this bit over here. It is reminiscent of the normalization term that we had, where we have pi sft exp reward over beta, pi ref as is sft exponent reward over beta, right? That's the normalization term that we extracted. Yes.
That part, they get the zx.
Yeah.
They specifically want this partition function to be the same as the normalized form.
As the probability distribution. The partition function just makes it it's a constant, a normalization constant that makes something a probability distribution.
And what do you mean by partition function?
That's just any constant dependent on x, which is input, and then the
Divided by the weights, some weights.
of not divided. It's the output distribution from the SFT raised to the exponent of the reward divided by beta. Beta is a hyperparameter.
So it's the reward, e to the power of the reward, divided by some constant. And then that will become times the pi ref.
Yeah.
That will become the partition function.
Yeah, that will make the probability distribution a partition. That will make this output over here a probability distribution.
It will make this part a probability distribution.
Yes.
What probability distribution?
Equation 8.
Because equation 8, if I look at the algebra, if I take the in the denominator, if I take the 1 over zx out of it, it cancels out, right? Minus log is zx.
Yeah,
And
that
then
it
if I
cancels.
If I take the denominator, if I take 1 over zx out of it, it just cancels out.
It just cancels out, correct.
But so technically,
it
can be anything.
Yes.
It can be anything.
Yes, it is. It can be anything. It can be anything because it's just a constant that makes it a probability distribution, right?
Yeah.
So
we specifically want it to be certain form.
yeah, and the important idea is that it is only reliant on x, which is input, which will be very, very important, right, in a second. But yeah, this is what we are doing, and then we transform this, or we get this new optimal policy, which is basically just the 1c of x. This is what the probability distribution is, not equation 8. Sorry, just the denominator of the KL divergence. This is our new distribution. So equation 9. That's a probability distribution. Yes.
Probability distribution of the output.
Probability distribution of the output accounting for reward.
Because equation 8.
Yeah, that's the optimization objective.
Is coming from the expectation of reward minus tail divergence. Just
Yeah.
that coming from that equation. Right?
Which we swap to KL divergence minus reward, because we change max to min.
Sure.
And then just reverse the order. So
Yeah.
it just became divergence minus reward.
Sure. So we do the from max to min.
Yeah.
And then from that on, we just do math to get to equation 8.
Yeah.
And then so equation 8 is the equivalent of the expectation of R5 minus tail divergence.
Exactly. Yes, it's equivalent. Exactly the same. It's just represented a bit differently, but it's exactly the same, right? This is very important because we get this objective or this new distribution that is a function of pi SFT as well as our reward.
So then
This is very important because it is a function of pi sub SFT and our reward.
it's always the case in the
Well,
original form.
yes, but as a probability distribution, because now the optimization objective was a function of SFT and the reward. Now we have a probability distribution that is a function of the SFT and reward.
Probability distribution of the
That's a function of SFT and reward.
reward.
Yes.
Sure.
Right? Now this is our new objective target language model that we want to obtain.
How do we so we call this the entire denominator as pi star.
Yes, because it is a probability distribution. We can compute KL divergence of over two probability distributions. The top numerator is our new model, and the target golden boy objective is pi star, right?
I see. Is it still a vector of
Yes,
30,000?
36,000. Yes.
It's still a vector.
It is still a vector 36,000. This time as a probability distribution. So now the requirements of a probability distribution are maintained. So every value is 0 or above, and the sum is equal to 1. This is the new thing that we have obtained from that pi star will follow, which is very important. So we have that. Now we can log both sides and then solve for r sub x comma y. So we gain our reward model, or we actually calculate what our reward model should be, and then we get pi star y sub x over pi SFT y sub x plus log z of x. Z of x now again still is this thing that we cannot actually compute, right? And that is a problem. So if we go over here, yeah, we have this partition function over here. We still cannot actually compute this, right? It's a very complicated thing to compute. We don't have it yet, but because it's still unsolvable, but it's hard to approximate z of x. However, we can fit this to our Bradley-Terry model, which we call from earlier was the softmax of the output. So we discussed this over here, this bit, right? We get the value over here. This requires the reward function, but the important idea here is that since z is only a function of x, does not rely on the preference at all. The derivative of it relative to the actual preference is 0. And during optimization, it does not play any role. So we can effectively ignore it.
Ignore what? Ignore the zx?
Yeah, ignore zx. So if we fit the reward model that we have obtained to the Bradley-Terry approximation or the Bradley-Terry representation, we have the pi softmax, then of just actually y1, which is not represented over here. But either way, we have. Oh no, this is not correct either. This is not softmax. This is ReLU. Equation 11. It's ReLU. My bad. But wait. Let me just check with the paper. I think I'm getting something wrong here. Yeah, we do have this equation 16 into 17. Okay, yeah, I guess it is ReLU at the end of the day, but the derivation from that I am not exactly sure. This is here. This is the actual derivation from it. The equation, this equation, we go from here to here, but it's just not as simple as just plugging R star. We have the R star, and then R star over here. Okay, well, in that sense, that's correct.
We can cancel out the ZX because we do the.
Okay, I guess I don't understand the last step, but the remainder of the idea is the same. Sorry. So we have the R star that we have calculated as a function of the partition function, the supervised fine-tuned model, and then plus beta log of the partition function, right? Now from there we substitute into the Bradley-Terry, we substitute the reward into the Bradley-Terry model. Then the rest getting to the second to last step is just algebra, correct? But from there to the last equation, I am not exactly sure what's happening.
Which one?
I don't know what the activation function is over here that converts the entire thing from
Similar, right? Isn't it the formula?
Is that? Oh, it's that sigmoid. Oh shit! Yes, you're right. It is sigmoid. Yeah, it is sigmoid. Exactly, it's sigmoid. That's the one. Yeah. So this is the sigmoid function. Thank you. Okay, that is very helpful. So that's how we go from the reward function to loss over a single sample, and then we can basically calculate the log likelihood of or maximize negative log likelihood using MLE in order to get the loss function for DPO, and that's how we get our language model at the very end.
Yeah, to just backtrack a little bit to
Yeah.
have the whole picture. In the equation 9, maybe in the previous slide, equation 9, we actually try to solve. We call the entire denominator pi star, right? We call that pi star, and then we try to solve for r x y using pi star. Going from equation 9 to equation 10.
Yeah.
We just try to solve for the r
Yeah.
x y.
Yep. Yep.
I'm sorry.
You're good.
Yeah. So going from 9 to 10, and then we try to plug equation 10
Yeah.
into the Bradley-Terry model because as we see on the projector over there,
Yep.
e to the power of 1 divided by e to the power of 1 plus e to the power of 0, right?
Yeah.
We basically plug this
But just for y sub 1. So just for y sub 1.
y sub 1.
Yeah. So only for the winner. Only for the winner. So we have y sub 1 softmax. We are getting a scalar output.
Scalar. We're getting a scalar output, sure.
Yeah. So
We
we
take the max, and then
yeah.
uh,
We want a scalar output, so we just pick the winner, the probability of the winner. Even though it's binary, we just pick probability of winner.
winner.
Yeah.
And then the other one is just e to the power 0.
Yeah. I didn't follow. Say that one more time. Yeah. The other one is just e to the power 0.
There are two of them, right?
Right.
Winner, loser.
Winner,
and
loser.
then we pick the winner.
Yep.
The other one is wherever it is, it's a loser.
Yeah. Yeah. That's just e to the power 0. Correct. We don't pick the loser. So we don't pick e to the power 0. We pick e to the power of 1 over e to the power of 0 plus e to the power of 1.
Yeah, and then we substitute the 1 with equation number 10.
Correct. Substitute the 1 with
Equation number 10.
yes. Not we don't substitute the 1. We substitute r star with equation 10. We substitute r star with our reward, right? So r star is there over here in equation 3.
Yeah.
We substitute that r star with the reward that we just calculated, and then we get the sigmoid of the of basically just the replacement and then a bunch of algebra that is demonstrated over here. This bit.
Okay, so but there is y1 and y2.
Yeah.
So it means there is a winner and loser, right?
The winner and loser is both represented in the reward function, but the denominator of it, right? We only pick the winner because we have a vector field. We have the vector of the winner and the loser. We only pick the value of the winner, but the winner values also consists of the sum below, right? For softmax, the denominator is the sum of the exponent of the what do we say, of the winner and the loser, right? We have exponent of, like over here 16, we see exponent winner, exponent loser,
Yeah.
right? Or exponent reward winner and exponent reward loser,
Yeah.
and then exponent reward of winner is the numerator, right? Softmax would be exponent reward winner, comma exponent reward loser, and then denominator stays the same in both cases,
Yeah.
right? We are only picking the winner.
But the denominator is composed of winner and loser.
Yes, correct.
How there's so many losers? What do I pick?
Oh, under Bradley Terry, we have only one winner, one loser, because the preference model is is choice between two samples, correct?
I see.
So you have only one winner and one loser.
Yeah. So human is still in the loop. but
Human is used to create the preference data set, which is the same as RLHF,
Yeah.
but the difference here is that instead of the PPO, you are using MLE.
And the MLE LDPO is what? So there's a loss function, right? There's a loss function.
Oh yeah. So that's just negative log likelihood over the preference function. So we've managed to get this in closed form basically.
LDPO is the loss function we want to minimize.
Maximize, because it's negative log likelihood.
Want to maximize. And then what is the final form of that?
Let me see if I have it over here. No, I don't. Here, this is the, yeah, I do have that, right? They're basically just this. Yeah, but
It's a sigmoid.
more
log-
explicitly.
Log sigmoid.
Yeah. It's just log likelihood, because we have probability distribution and we just compute negative log and then that's our likelihood, right? And then we maximize the log likelihood to use or to get the optimal model.
Intuitively, does it make sense? Right now, we're taking the winner and loser.
Yep.
We're trying to make them also far apart.
Oh yeah, so here's the mechanistic breakdown of it, which is actually quite helpful. So we have the DPO update, right? The gradient that we compute over the loss function. That gives a higher weight over
It's
the.
also confusing here. Right now, the R is coming up again. When we're looking at the gradient, we get rid of the R.
Here. This is just it's this. We created this optimal R.
Oh, so this R hat is different from the reward hat. Sorry, different from the reward we talk about.
Yeah, it's not reward function. And I think, this is my personal opinion, but I don't like the notation that they have used over here, because when we use R sub theta, I thought it was parameterized.
Yeah.
But that is not, technically it is parameterized, but parameterized by the SFT and the
Not the same.
and pi theta,
Not the same.
which is exactly, it's not the same.
Yeah.
So yeah, but the idea here is that we are using that reward function, which is thus theta target model, SFT default model, and that's really all that we need, because we get this higher estimate when the higher weight when the reward is incorrect. We want to increase likelihood of the winner, decrease likelihood of the loser. Fundamentally, it's not doing something that feels insane, but it is internally embedding the reward function,
Yeah.
which is what makes it so efficient.
But it says higher weights when reward estimate is wrong. In the
Yeah, first bit.
Yeah, higher weights when the reward estimate is wrong. But right now we're taking the derivative of the DPO of the LDPO, right?
To theta, right? Derivative of loss to theta.
That's right. So it's a derivative, and we want to do weighting descent. We try to make the derivative equal 0.
Yeah, but I mean, if you read the para, right, it says gradient of the loss function increases likelihood of preferred completions and decreases dispreferred completions. The examples are weighed by how much the implicit model rates the dispreferred completion scaled by b. So the reward model or the internal reward model dictates the scope of the difference. So if the implicit reward model gives us, let's say, a -5, right, over here, reward.
Because
this is R star that we are effectively approximating. This gives us -5, and we are like, this is very, very bad. I hate this response, and I do not want to see it ever again.
Yeah.
This is a very negative model, which is why the gradient update will be more aggressive. If it is -0.05 and it's okay, then the gradient update will be a lot more passive.
Okay. So it's a secret reward model.
Yeah, implicit, exactly, implied.
Implies can we see this in that equation?
Uh,
That's right. R hat
Yep.
is a log of pi theta divided by pi width.
Yep.
Does that mean this is our reward?
That's our reward model.
Secret reward model.
That's our secret reward model.
And R hat doesn't show until we calculate the derivatives, because we never see that form.
Yes, exactly. We never see the form before. That is pretty cool, no?
The secret reward model. I missed out on one.
Do you want me to roll back?
Just a bit.
Where did you miss out? Where should I go back to?
We're looking at DPO and we just replaced tail divergence with.
Can you tell me what equation and what page?
Yeah, just go back. Okay, yeah.
Okay, so we have the overall objective that we want to achieve is we want to transform the loss that we are calculating over the reward. So instead of maximizing reward, we want to actually maximize the loss over the policy, right? Because the reward is a proxy of the actual implicit policy that we are trying to optimize against. So that's the overarching objective that we are trying to face here. So first, in order to do that, we have to identify pi SFT, we already know pi SFT. We have pi SFT and samples from the optimal reward, but we want to get pi star, which is a probability distribution that contains both pi SFT and R. So we need to get the optimal probability distribution, which is basically the target label, right? By using the optimal reward and the supervised fine-tuned model. So that's the overarching goal. We use that idea to construct a loss function which just maximizes over negative log likelihood, which maximizes negative log likelihood over KL divergence of pi sub theta, which is the model we want, and pi star, which is our ideal model, to get the new supervised fine-tuned model.
Okay, I'll take it very fast. But the gist of it now is that we are a
Mhm.
This guy is still not differentiable.
This guy is pi theta is differentiable. Pi theta is our final model, right? The thing that's not differentiable is the reward function, right? The parameterized reward function, because it's not continuous,
Yeah.
right? So we are basically bypassing this reward function by creating a new ideal probability distribution as a function of optimal reward and the original supervised fine-tuned model. If we are able to create this new or this new probability distribution, we don't really have to care about this reward model, because we already have embedded the reward function as part of the update to the probability distribution. So let's just assume we have this token or like this vocabulary, and we have this one token that's very prominent, and then a few other less prominent tokens, and then others are close to zero, right? Now this is the cat and this is dog, right? We want to change the weights, or we want to change the probability distribution. So we want this probability distribution to remain the same, this probability distribution to change drastically to lower, and this to increase drastically. So we have this is our dog and this is our cat, and then the rest remains more or less the same. Now if we are able to do this transformation, right, or create this transformation, our problem is solved, because we have this transformation. We just perform MLE over this to get the optimal model. That is supervised with the preferences embedded. So this process is getting pi star from pi of SFT and the optimal reward model. Okay, so
How do we get the R? We get the pi SFT, of course.
right,
But the R.
we calculate that when we embed it into Bradley Terry. So in the next slide, right, we have this restructuring the maximization objective, right? We go from the maximum, which is this is just the algebraic difference, right? And zx is the partition function, so we will not worry about this because it will disappear during gradient optimization, because derivative of constant is 0, and zx does not depend on anything does not depend on y or the output of pi SFT, right? So when we compute the gradient against theta, right, not y, against theta, it is 0 because it's not involved. So we don't have to worry about that. Okay, so keep that in mind. But besides that, the overall transformation that we're doing over here is as follows, right? We have maximization objective from the RL approach, reward minus KL divergence, right? We transform maximum to minimum from 4 to 8 by just reversing it. So we go from KL divergence minus the reward, and that makes our maximization objective a minimization objective. And then we combine the reward and the SFT model by plugging in the partition function. So if we look at the appendix, that talks a bit more about it in better detail. So A1 here, that's A2, right? So this goes in step-by-step order, where we did the transformation from the maximization to minimization, and then over here we plug in the partition function, right? And the partition function is defined as follows, right?
Okay.
So now this denominator over here, right, this is our new probability distribution. This entire transformation gives us pi star, and pi star is represented by this denominator over here, right? Now once we get this pi star, right, we have this thing. It's still we still cannot compute this because it's z, because we have the z of x term and we don't have this reward output yet, but we do have the ideal probability distribution in closed form, correct? This is very important. So now we simply solve what? Closed form is just can be represented as a single equation. So if we were to try and represent loss of the reward as a single equation, we cannot do that because it's non-continuous, right? This can be represented in closed form. So we have we log both sides and then solve for r x comma y, which is our reward function, correct? So we get this reward function equal to beta of log of the ideal distribution divided by the supervised fine-tuned distribution plus the log of partition function, right? And then from here, it's still technically unsolvable. We cannot it's hard to approximate the partition function, but we plug the reward into Bradley Terry, and then during the gradient descent, z of x just disappears. So this is a Bradley Terry, which we discussed in the starting with the ranking method, right? We have the binary ranking method where one is better than the other, or we rank like 10 different options, right? So this paper does the derivation for Plackett-Luce, which is the n-many, as well as the binary. But for now, we're just discussing binary. We have the equation 3, which is the Bradley-Terry model, which is the softmax of the reward over x comma y, and the derivative of z of x to not d of y to d of pi sub theta is 0. So it doesn't play a role in the optimization. We can therefore technically just go ahead and compute it. So if we plug in that reward function, we just get this new equation, which skips a bunch of steps, and the sigmoid softmax is wrong. It's actually sigmoid. It's not softmax. But if we go over here, they show it, and it becomes very obvious to see, right? We have the R star. This is our optimal function, correct? The optimal reward that we have been able to express as a function of optimal policy pi as well as SFT plus log of the partition function.
Okay.
Correct? Now we plug this into the Bradley Terry, which is just the softmax, and we take the winner value, and we get like the reduction from the first step and the second step is just algebra, right? The last step, 1 over 1 plus exponent, is the sigmoid definition of sigmoid function. So we get, I can show you the sigmoid. Even I did not get it. We just literally cracked this during the thing. Wait, 11. Do I have it here? No. Oh, the rest is just results. We will fly through the rest. This is the function of sigma. This is the reward. This is the sigmoid function, right? We just literally plugging that in. That's it.
Okay.
So we have that, and that is the probability over the single sample, and we just maximize expectation over the negative log likelihood. Negative log likelihood is a loss function. Then we get DPO, and that's our MLE.
Is the P
After we finish optimizing over DPO.
Is the P star here the same as the pi star?
P star is not pi star. P star contains pi star.
But go back to this picture. So we have one distribution. We want to have like a golden distribution to optimize.
I didn't realize
from,
it was so dark. Sorry.
Yeah. So we have original distribution. Cat has more probability than dog.
Yep.
And then we want it have the other way around.
Yep.
And then so the other way around is the golden distribution we want.
Yeah.
And we said that we want to get that distribution instead of calculating a R phi
Yes.
instead of a reward function. Right?
Exactly. Yeah.
And right now our goal is trying to get the pi star. And here, are we getting the pi star somewhere?
Yeah, we get pi star over here in the expectation in equation 9.
But this is still, pi star is still a function of R.
Yes.
So
We use that to solve for reward and then plug that in. Pi star is the optimal distribution.
And then, yeah, we
It's-
go from equation 9 to equation 10. It's
Yeah.
just algebra, like we just solve for R.
Yeah, we just solve for R. Exactly.
And then we plug that into the Bradley Terry model. Right?
Yep. Yeah. Right there.
It's and then it becomes our P star.
Yes.
And then we never solve for pi star.
We obtain pi star. We don't need to solve for it.
We obtain pi star.
Yeah.
But pi star is supposed to be a vector of 36,000.
Yeah. Given input. So wait, let me see. There is a better, more verbose explanation of that. The appendix proof. Two reward function. No, there's a different one.
Because the big picture is still a little bit vague at the very end.
This section we derive the gradient of DPO, but we have pi theta pi f. So we are representing it at the end as a function of pi theta and pi f. So pi star is not included in the final one. Okay, I see there is confusion here. That makes sense. Okay. Let's see what I probably just got it wrong, or like copied that thing wrong. Okay, yeah. So over here, right, up to this point, we have optimal policy, pi star, and reference policy, pi ref, and then the optimal RLHF policy, pi star, under Bradley-Terry satisfies the following preference model. Then we have the probability of preference data from in terms of optimal policy rather than reward model. So we formulate the objective. Analogous to the reward modeling objective is in equation 2, which is this, the log of reward of the winner minus the reward of the loser. So it basically considers the reward function as pi theta over pi s of t, and the loser pi theta pi s of t, and that is what they plug in and get into the final thing.
That becomes the pi star?
That they get to represent pi star, yeah. They don't actually end up showing pi star, they convert it over here. Where we go from equation 6 to 7, pi star disappears and it becomes pi sub theta, right? So we have pi star, which is optimal policy, and pi theta, which is what we want to approximate, the optimal policy. So pi star is goal. Pi star is the goal. We have the reward function that is implicit within pi theta, and that is represented as this final loss. Does that make sense? I'm trying to convince myself beyond just convince you, but yeah.
What's pi ref, real quick?
Pi ref is SFT, pi SFT. So you can use any reference model. They remember how they said that you can use SFT instead of you can just fine tune the over preference data instead of if you don't have SFT model over a good data set in the starting. It's basically just that.
Okay.
I also did not realize we are at 1 hour 37 minutes.
Yeah.
So okay. Thank you. I am going to very much just hand wave over the results, right? We have the following tasks: control sentiment generation, text summarization, and single turn dialogue. GPT-4 was used to perform auto evaluations on the data, but that's I don't know, I think that's a little bit lazy, but anyways, overarchingly it shows that DPO works. The theory shows that DPO is able to optimize equivalent to RLHF with performance equivalent to RLHF and much faster. IMDb shows that very well, where the reward is capped out very early on, and then it basically is static, while all of the other PPO methods are much slower to optimize to the final reward while maintaining KL. While maintaining KL low, it is actually, they don't do it at all. While the reward model is able to do it very easily with the minimum KL divergence, so it functionally works very well. Scalability, it has been shown to work well at scale, outperforming PPO without fine-tuning the hyperparameter, and they also use human evaluators to compare for robustness, and generally it is outperforming the rest, which is fantastic. So for generalizability, they also compared PPO on out of distribution inference, and even in that case, it outperforms PPO. And they say that more a more extensive study on the generalizability of DPO is required, as well as the scaling of DPO, since it was only evaluated on 6 billion parameter models. So an exploration of its performance at scale is also necessary. And that is the final thing that I had. I hope this was helpful. Thank you very much. Have a great rest of your day.